all these very nice hardware systems, all these robots that we want to deploy are increasingly going to have lots of software inside them. And if you care about any of the terms in blue on the left-hand side there concerning your software, whether it's transparent, safe, reliable, responsible, reconfigurable, secure, or you want to get it certified, then you're likely to have to need some verification and validation. So I'm just going to give a very, very brief introduction to that, a little bit of introduction to architectures, and then move on to more technical talks later on. I won't go through all these ones in lots of detail. So verification and validation in a nutshell. Can you see my mouse? My hand, in fact. So a very broad idea. Somebody, a user, a developer, a vendor of some form, says they want a particular system to do something. We capture the requirements of what that person wants in some sort of specification. It'd be nice if the specification was very precise, but often they aren't, and often they're English specifications. So this specifies what the system you're trying to build should do. Then somebody implements the system. And then the question is that system that you've built, does it match your specification? And that's what verification does. It's trying to match the system that you've built, whatever it is, whether it's a piece of software or even a piece of hardware. Does it actually match the specification of what you said you wanted? And then validation afterwards is checking that the system you've built is actually what the person wanted in the first place. And that involves just essentially a lot of dealing with the person and saying, is this the right type of system? And there are a lot of different techniques for doing either verification. Sorry?
Michael, I'm sorry, but I think you're stuck on the title slide.
Again, okay. Sorry about that. I won't go full screen.
Okay, now we can see the...
Right, I will not go full screen then. Okay, so, yeah. So did you got all that? So going from some description of what you want the system to do, which is specification, to the real system, and then verification is checking that the system matches the specification. And there can be lots of different ways of doing this verification. I'm not going to go into all these in detail. Very formal proofs where you give mathematical proof that this system actually matches its specification, or testing the system to show that it matches the specification, either in simulation or in real physical testing. And then validation is often checking that the system matches what the originator wanted, and that can again be physical testing. You just test it and make sure it looks like what the person wanted, or actually ask the person, is this what you wanted? Does it do what you think? And does it match the test scenarios that you had? And for those of you who like phrases, these are the typical phrases people use. Verification is, are we building the system right? So does the system match what we wanted to build? And then validation is, are we actually building the system that the person wanted in the first place? Are we building the right thing? So that's a very, very sort of broad introduction, verification and validation. And what we typically do at Liverpool is a mixture of simulation-based testing and formal verification, and we'll see a little bit of this later on. Let me just say a little bit about some of the differences between testing and formal verification. I know a lot of people use testing in various forms. So let's imagine your favorite system has lots of ways it can run depending on its environment, depending on its activity. So there are lots of different execution paths it can run, any of these routes down this tree. And we want to check whether each of these possible executions match some requirement. Are they doing the right thing? And so we could test this. And testing typically selects some of these routes through this tree. In this picture, it's quite a lot of routes, but in reality, it's usually quite a small number of routes. And so the pink ones are the ones we're going to check, whether they match the real property or not. And we can check whether each of these test runs matches a particular property and give it a yes or no answer. And if all those tests match, we say we've tested it, and all these runs match the requirement. Formal verification, the idea is to capture all possible runs. So have some way of capturing all possible runs of the system and be able to check the properties of all those possible runs. So clearly, if it's an awful lot of runs, this gets more difficult, but you're more confident in the behavior of the system with a formal proof. So the formal verification we typically do has some advantages and disadvantages. The advantages are, as in the last picture, that this covers all the situations. So if you do a formal proof, you can guarantee that all the situations you represented will have this property. You can also do things like, rather than just saying, I'm going to test a scenario and see whether it satisfies the property, you can flip it the other way around and say, which sort of scenario would make the property fail? And you can do that with formal verification as well. So rather than just testing and seeing what happens, you can say, what would I have to do to make this thing go wrong? And work backwards. Clearly, it's not all fantastic. There are some problems here. So formal verification is quite expensive and quite difficult. So it takes a lot more effort than testing. And also, if you're dealing with real-world systems, like robots in an environment, then probably you have to do some abstraction analysis, because the tree that you have here, this tree, is very big. So you can't really capture it all in detail. So you have to do some abstraction analysis. So there are various different techniques, and they have those benefits and advantages and disadvantages. Okay. Doesn't mean you can't use several of these things. So this picture is trying to give you an idea of, there's lots of different verification validation techniques. Think of the brown boxes up here. Going from things like formal verification, which takes a logical requirement and matches it against some description of the system and gives you very high confidence, but it's probably quite a long way from reality, all the way up to a practical test in a real scenario, which gives you a lot of confidence that it works in that scenario, but gives you very little confidence that it works any other time. In between that, there's things like simulation-based testing, where you try and build a simulation of the system and the environment and run through lots of tests in a virtual way. And again, that's you're not as confident, you don't have as strong guarantees as formal verification, but it's a lot more practical, a lot more realistic than formal verification, but still not as realistic as the real system. So there's a whole bunch of these things. I've only put 3 here, so lots of different verification techniques you can use. And often what we do is mix them all together and use them all in different parts for the same system. Okay, so that's just a very broad idea about verification and validation, which we'll hear more about from Raphael and Fabio. Just wanted to say a little bit about architectures. These autonomous systems, robotic systems, are not just a big flat piece of software, not controlled by a big flat piece of software. They often have quite complex architectures inside, and many of you will have seen or used modular architectures such as ROS or ROS Industrial or ROS2. There are lots and lots of these things. There's new standards coming out on modularity, for example, this ISO standard that's going to be out soon on modular architectures. And these things are useful for obviously separating the different parts of the system, make it easier to engineer the system, but also, as I'll show in a couple of slides, makes it easier for the verification that we want to do as well. So separating out the different components of the system and being clear about what they're doing is very important. Another important aspect to do with architectures is transparency. So again, there are standards. I mentioned this at the bottom here. There are standards being developed related to transparency of these systems. So not only do we want a modular architecture, we want the components in the architecture to be transparent. We want to know what they're doing. We don't really want a black box. We have no idea what's going on in there. We have some idea of what this system is trying to do. So transparency is important as well. The other aspect that is relevant, again, back to verification, is not just modularity and not just transparency, but having some idea of each of the components. What are they trying to do? What are they supposed to be doing? Essentially having some specification. If you remember the picture several slides ago, when you write down your requirements of what your system should do, it's a specification of what it should be doing. You can do that for all of these different modular components. And this is important for things like verification, because if we want to verify a system, we don't want to verify the whole lot at once. We'd like to separate it out and verify each of the components separately, possibly using different techniques. We might test one of these components, formally verify another component, etc. But for each one, we need to be clear, what is it trying to do? What's the precise specification of this thing, where we can. So when we have modular architectures with precise specifications here, we can do lots of different verification, and potentially in very different ways. And I'll show a picture in a couple of slides' time, gives you an idea of what sort of verification we do. So verifiability is important, not only to have modular components, but have have a description of what you think that component is actually doing, the software is actually doing. Another aspect to do with architectures is responsibility. That might sound a very strange thing to talk about, but when we delegate some key task or key responsibility to our favorite robot, we need to know where those key decisions are made. Where is the responsibility for those decisions? So not only do we want specifications of each of these components, we want to identify where the key decisions are made. So maybe this component here, this agent, might be making key decisions about safety or something like that. Another one might be making key decisions about privacy or security and what information can be passed on. So that becomes important as well. And again, it's all to do with the type of architectures that you build. I'm conscious that I'm running out of time, so I'm on almost the last slide. So architectures are important. The particular work that we do is relates to, it involves architectures where there is a distinguished sort of component inside, a separate component that makes the key high-level decisions. So the key decisions that a human operator used to make, if you then make this a fully autonomous system, then this bit of software will make the decisions. And this thing is typically called an agent, and it's going to make the key decision about what to do. The big decisions, not the sort of low-level detailed decisions about how many millimeters to move one gripper, just the larger decisions about what to do, when to do it, etc. And that will interact with lots of other subcomponents, which I've put together here in terms of feedback control systems to do with object recognition or locomotion or any of those different planning aspects. So the systems we build, we analyze are typically like this, and we can use different techniques for different parts. We can use formal verification for the agent to prove that it makes the right decisions at the right time, and then other things like simulation or testing for the feedback control elements, and maybe some runtime monitoring as well to check that this system is doing what we expect as we go along. And the whole thing, we can do some practical tests to give confidence that this thing is really doing what we want. So there are lots of different verification and validation techniques that can be used, not only on whole systems, but on different components within the modular architecture. And hopefully in the next couple of talks, you might see a few of these things appear. So I think I'll stop there, which is possibly 15 minutes. Helen?
Yeah, that's brilliant. Thanks, Michael. We've already got a question in on the chat. So
okay.
Is part of your work then to verify the level of autonomy through the verification of the agent's decision-making?
In a broad sense, yes. It's quite hard. Level of autonomy is a very vague thing. It's nice to write it down in English, but it's quite hard to be precise about those things. You have to be maybe very precise about what responsibility this thing has, what tasks it's going to do, when it's going to do them, and then prove that it will actually do those things in the right way. Just saying that it's level 2 or level 3 isn't really going to help us very much. But yes, you can do that verification. And certainly when you get to higher levels of autonomy, you need to make sure that the way the system makes decisions, which is captured in that agent, is verified, and you're sure that it will make the right types of decisions when there's no human controlling it.
Brilliant. So I don't think there's any more. Oh no, there is.
Okay.
Hi Michael, I am from GMV and we are working on V&V for space robotics, building a distributed simulator. Very interesting talk. What is your view on benchmarking system, so beyond V&V comparing systems?
I think it's a very good thing. I'm not sure how to do it. I think it's very hard to come up with benchmarks that aren't biased towards particular techniques.